Hi, this is the second video on complex numbers, and in this video I'm going to discuss how we can visualize the geometry of complex numbers, and then also how we can express complex numbers in something called polar form. So, what is this Argand diagram in polar form? Well, let's start out again by considering real numbers. So you know how to visualize real numbers. You put them on the real number line, which is oftentimes just denoted as the x-axis in a standard graph with x and y axes. And so the negative numbers go to the left, positive numbers go to the right. And this is how we visualize the real number line. With complex numbers, there's a real part and an imaginary part. So a complex number really consists of two real numbers. And we can plot those two real numbers on a plane. And this is how we visualize complex numbers. And so we take the real part of a complex number and the imaginary part of a complex number, and then we plot the complex number a plus bi with x coordinate given by the real part and y coordinate given by the imaginary part. And so any complex number will be a point on this plane. So this visualization of a complex number is called the Argand diagram, oftentimes in engineering, or sometimes the complex plane is probably more the mathematical term, the complex plane. And this is how we should understand the geometry of complex numbers. One comment I'd like to make is that people oftentimes think of complex numbers or imaginary numbers as being very abstract, difficult to understand, and something that aren't useful, but this could not be farther from the truth. Complex numbers are actually very useful in many applications. They just have this very unfortunate name of complex numbers, which makes them sound more complex than they are. Especially imaginary numbers. This makes them sound like they're somehow not a real thing that is worthwhile studying. But complex numbers have many applications, and you can visualize them just like you can real numbers on the complex number plane rather than the real number line. So if we think about adding some other complex numbers in here, we can visualize some specific ones, like -1 plus I. So the -1 is the real part, so it's x coordinate -1, and 1 is the imaginary part, so y coordinate 1, and the same number with the different signs in front of the 1 or I, just to form the four corners of a box. Here's another complex number, 2 plus 0.5i, so the x coordinate is 2, the y coordinate is the imaginary part, 0.5 or 1/2. One thing to notice here is that we have a geometric interpretation of what we mean when we take the complex conjugate. So we take the complex conjugate of, say, -1 plus I, you change the sign of the imaginary part, you get -1 minus I. And this is just flipping the complex number about the real axis, or the x-axis. And you can see we have other complex conjugate pairs, 1 plus I, 1 minus I, or reflections across the x-axis, and 2 plus 1/2 I, 2 minus 1/2 I, also reflections across the real or x-axis. All right, so this is the Argand diagram or complex plane, how we visualize complex numbers. Since we think of complex numbers as points in a two-dimensional plane, we can express them by either their x and y, Cartesian coordinates, or polar coordinates, like we've discussed before. So say we have a given complex number, z, and its real part is x, the imaginary part is y, so x and y are real numbers. Then we can express z using polar coordinates instead, so using r and theta. R is the distance from this point in z to the origin of the complex plane, and theta is the angle which is made with the positive real axis. And if we write the real and imaginary parts, the x coordinate is the real part, r cosine theta. The y coordinate is the imaginary part, r sine theta. And so this is really just polar coordinates in a kind of disguise of complex numbers. And we can write complex numbers in this form, and we call it the polar form for a complex number. The polar form for z. So how do we determine r and theta for the polar form for a complex number? Well, this is really just polar coordinates for points in the plane, which we've looked at before. And so r is the modulus of z, that's the distance from the origin to z, square root of the real part squared plus the imaginary part squared. You can write this as z times the complex conjugate of z. That's the modulus squared, as we've discussed in the past. If you multiply all this out using the rules for multiplying complex numbers that we discussed last time, then you just get r squared. This is something we covered last time. And so r is the modulus. And theta is called the argument, usually, of the complex number. And so this is just the angle in polar coordinates. And so there is some ambiguity in defining the argument, because when the angle increases by 2 pi, you get back to the same point. And so this does cause some problems when we're thinking about complex numbers. But in order to specify a specific argument for a given complex number, we require that the argument has to be in the interval from negative pi to pi. So negative pi would be the angles that go down this way up to the negative real axis, and then positive angles up to pi would be the angles in the upper half plane, the upper half of the complex plane. And so if we require the argument, the angle theta, be in this interval from negative pi to pi, then theta will be uniquely determined. If we don't require that, then we could add 2 pi to theta, and we get another angle, which could also work. All right. So the modulus of a complex number, we know, is easy to work out. You just take the square root of the sum of squares of the real and imaginary parts. This is really just the same as the length of a vector in 2 dimensions. But the argument can be more complicated, although it really is just finding the polar coordinates for the point described by the complex number z, with the given real and imaginary parts being the x and y coordinates. The complication in finding these arguments comes from the fact that there's no single way that works for all angles to find them. You have to break up the plane into the quadrants and then consider which quadrant the complex number is in, and determine from that how you should determine them using trig functions. So I usually think it's easiest to find them using the tangent function. And the ambiguity comes from the fact that the tangent of a given angle is equal to the tangent of the same angle plus or minus pi. And so, for example, the tangent of pi over 4, 45 degrees, is the same as the tangent of negative 3 pi over 4. And so if you have a complex number that lies along this line that makes a 45-degree angle with the positive x-axis, then the argument could be either pi over 4 or negative pi over 4. And to determine which one it is, pi over 4 or negative pi over 4, you have to think about which quadrant the complex number is in. So for example, we have the two complex numbers, 1 plus I and negative 1 minus I. The argument for 1 plus I would be pi over 4. The argument for negative 1 minus I would be negative 3 pi over 4. But if you took the tangent of the imaginary part divided by the real part, it would be the tangent of the argument in either case, the tangent would be the same in both cases. 1 divided by 1, the tangent of pi over 4, is the same as negative 1 divided by negative 1, the tangent of negative 3 pi over 4. And so you need to consider which quadrant the complex number is in order to determine the argument. So the tangent will be positive in the first quadrant, negative in the second quadrant, positive in the third quadrant, and then negative again in the fourth quadrant. All right, so as an example, let's find the polar form of this complex number, z equals 1 minus the square root of 3 times I. All right, so let's first plot that number on the Argand diagram. So z is 1 minus square root of 3 times I. Draw the complex plane or Argand diagram. So what's usually the x-axis is the real axis when we're thinking about complex numbers, and what's usually the y-axis is the imaginary axis when we're thinking about complex numbers. And so let's make some ticks here. So this will be 1. So the real part is 1, so that means the coordinate on the horizontal axis is 1. And the imaginary part is negative square root of 3 is around negative 1.7, so about here where this z would be. This complex number 1 minus square root of 3i. All right, so r, the modulus of the complex number, is the distance or the length of this line here, and theta is going to be this angle here. So it's going to be a negative angle. It should be a negative angle between 0 and negative pi over 2. Okay, so let's first find the modulus, r. For the polar form, r is going to be equal to the modulus of z, and that is equal to the square root of the squares of the real and imaginary parts. So the square root of 1 squared plus negative square root of 3 squared. It's the length of this segment right here. The distance from the point to the origin in the complex plane. And so that's just the square root of 1 plus 3, so square root of 4, or 2. Right, so the modulus of this complex number, the distance from the origin in the complex plane, is 2. Now we need to find the argument, theta. So I should label this. This is the modulus. Now let's find the argument. Alright, so to find the argument, we want to use trigonometry. And so we look at this triangle. And the theta is the angle between the x-axis, positive x-axis, and the hypotenuse of this right triangle. The tangent theta equals, well, the opposite side is this side. That's the the imaginary part is negative square root of 3. Divided by the adjacent side, which is the real part, which is 1. So the tangent of theta is negative square root of 3. And in this case, if we simply take the inverse tangent, we're going to get the correct angle. The inverse tangent gives you an angle between negative pi over 2 and pi over 2. So theta is equal to the inverse tangent of negative square root of 3. It's negative pi over 3. Okay, so now we have determined the modulus of this complex number, which is 2, and the argument, which is negative pi over 3. And so we can write down the polar form. So let's go back to the slide where we find what the polar form was. And the polar form for this complex number is 2, that's r times cosine of theta. Theta is the argument, so cosine of negative pi over 3 plus I times r. R is again 2 times sine of negative pi over 3. Okay, and so if you write in the values of cosine of negative pi over 3 and sine of negative pi over 3, you see you'll get back this complex number, 1 minus square root of 3. So 2 times cosine of negative pi over 3 is 1, and 2 times sine of negative pi over 3 is negative square root of 3. Okay, but this is the polar form where we write it as r cosine theta plus I times r sine theta. Alright, this is the end of this video. In the next video, we're going to continue on and discuss how we can use something called Euler's formula to write complex numbers in another form called the exponential form.